Hello everyone, welcome to my tutorial. My name is Han. I'm a research scientist at FAIR, and today I'm gonna give a tutorial with this title, Perceiving 3D Humans from Single Images. So before starting this tutorial, let's maybe consider why we are interested in 3D human perception. One of the very strong reason I have, or motivation I have, is to teach machines the way humans move. As you may imagine, humans move to achieve some physical goals and for communication. And we really want to make a machine to move like humans. And especially we want to do that by using some data, especially some 3D human motion data we collected from natural human behavior. And why 3D? Because 3D doesn't have any depth ambiguity. It captures the real signals in real environment, and there's no view or camera dependency. So that's the major advantage of the 3D. And essentially, we wanted to collect or capture this 3D human motion from in the wild situation where we can collect the real natural motions in very realistic scenario in various videos in the internet. So our fundamental goal here is to reconstruct the 3D human motion data from only 2D input images or any 2D input representation. And in pursuing this direction, one of the most important part in my thought is choosing the good and right representation based on the application. So based on the representation, maybe the problem became easier or more difficult, and maybe the 3D output can be more useful or maybe less useful. Then what kind of representation we can consider? In 2D domain, we can consider input image, a raw image, or to the key point. And in 3D, we can consider 3D key point output, 3D volume output, or 3D parametric model output. So let me maybe take some time to browse what would be the benefit, advantage or disadvantage of this 3D representation. So the first representation we can consider in 3D is this 3D volume or 3D voxel representation, where we have some occupancy information for each voxel location. This representation has this shape, which can be close to the target person. However, it doesn't have any correspondence information. So it doesn't have any temporal correspondence or correspondence across people. This dense trajectory information can have this temporal information by tracking one individual point over time. However, still it doesn't have any semantic information. 3D key point information or 3D skeleton information is also something we can consider as 3D representation. And in this case, we define a fixed number of 3D key points to represent each person. And in this case, because now we use this index key point for the representation, we can directly find the correspondence across people if we have this representation. So in this representation, we have correspondence across person, and we also have correspondence across time. So that's the major advantage. So this representation is actually really nice abstraction of human motion. Maybe one disadvantage is the key point is just maybe too sparse, so we don't have this volume information. And in considering this representation, we can also consider higher resolution. For example, by considering also face key point together, or even finger key point, which should be important in some domain where we need to measure some subtle gestures, for example. Another possible representation is 3D mesh representation. And in this particular case, we are talking a fixed mesh topology to represent each person. So in this case, now we have a fixed number of indexed mesh vertices by which we can actually find the correspondence across people. And in this case, we also have joint inside where we have 4 3D angle representation to represent the joint movement. So let's take a little bit of time to think about this representation here. So SMPL model is one of the most popular parametric model representation in the field. And parametric 3D human model means there is just a few parameters we can control. And by just controlling this parameter, basically we can represent this mesh human. So in this case, for example, in this SMPL, we have this mean shape, and we have this deformation space. and we have weight for each deformation shape space. So if you choose some beta weight here, by making some linear combination, we can represent arbitrary shape of person. For example, thin person, heavy person, and so on. And we also have this body pose parameter, which is controlling the joint angle of the skeleton. And this skeleton and mesh are linked by this linear blended scaling function, for example. So if we can change the skeleton, that also changes the mesh structure, mesh pose. And in the end, we can have a various shape and various pose by just controlling a few parameters, less than 100. So in this particular case, 3D reconstruction, human motion reconstruction basically means to obtain this parameter of this particular model. So we can basically make the problem much easier because this model provides a lot of interesting constrainability, for example, symmetry and so on and so forth. We can also consider some extension of this model. For example, in this case, ADAM model has also some additional expressive power for face and hands. So in previous case, SMPL model only can control the coarse body motion, torso and limbs. But in this ADAM model, now you can also control fingers and face and so on. SMPLX is another similar model, which is the direct extension of this SMPL framework. And once we have this parametric model output, then the output also can be usable for other applications such as user graphics pipeline, as in this retargeting example. So far we have browsed the possible 3D representation. And now let's consider our target problem from 2D to obtain 3D. And obviously, in this case, we need to infer this missing information, which is depth information. And this is fundamentally ill-posed problem, and we need something else to infer this missing part. So basically, we wanted to use some training. We want to train the model by using some data, so that in testing time, we can estimate this missing part, basically the depth information for full 3D information. However, there is just some limited amount of data we can use for this purpose because now our supervision is 3D, and 3D is often very tricky to obtain. So in this existing data set, usually they capture the scene in the indoor environment where multi-view system is available, and they can obtain this 3D supervision, basically 3D skeleton and so on. But our target goal is indeed in the wild situation. We want to use this 3D pose estimation for in the wild videos, for example. Then you can basically imagine this huge domain gap between this existing data set and this target domain. So how to solve this problem is maybe the core problem in this field. And maybe one exceptional case is this 3D data set where the data set is actually collected in outdoor environment using IMU kind of sensors. So usually in the field, this data set is used as a testing set, and other data set is used as a training set. And how we can actually solve this problem, this domain gap, for example. This particular example of representations can be one of the really good solutions. So in this example, we want to use 2D key point as input and 3D key point as output. And this work from Martinez et al. Is one of the most popular directions in the field. And the concept is actually quite simple. So we just consider a 2D input. 2D key point is input as a vector form, for example, and we consider to predict the 3D output again as a vector form, and to regress from this 2D key point to 3D key point. In this work, we just use fully connected kind of network. One good advantage of this approach is basically we can use this indoor scene because we are not using any raw pixel data. So input is just 2D key point, and in testing time, we can also extract 2D key point using any existing key point detector, and we can just use that key point for the input of this model. Because now we are not using any pixels, the domain gap between this indoor data set and in the wild scenes would be quite low. Although there exists some bias such as camera viewpoint, resolution of the indoor data set. Still, is pretty okay. Maybe the possible disadvantage of this approach is it's really dependent to the localization of this to the key point detector. If it has some error, that can be directly affected to the output. And also, because we're not using any image queue, there exists some fundamental ambiguity in this key point input. Another possible solution is now we want to use some dense pose annotation. And in this example, we consider to produce a 3D parametric model as output. A dense rec is one of such example. And in this case, the input is dense pose representation, where we have this IUV kind of dense correspondence map as input. And our output here is the parameters of the parametric model. So the good thing, similar to the key point input, here is we don't consider any raw image, but we are considering this representation. And this representation can be also estimated in testing time using dense pose detector, for example. So this domain gap issue can be somehow solved. Another advantage in this particular paper is this particular representation also can be synthesized from the synthetic data. For example, we can just use this mesh model here to represent this representation. Also, in this case, we have 3D supervision. So we can use this synthetic data without concerning about this domain gap or raw input data. But still, as it counts, this method is dependent to this, again, the quality of this dense pose estimator. Another possible option is using 2D key point as input and producing 3D parametric model parameters as output. SMPLify is one of such example. And in this particular method, we are not doing any user model training. This is more like an optimization-based method where in testing time, without learning, we optimize the parameter of this parametric model so that the error, 2D reprojection error between this given to the key point and the projection of the key point of the 3D can be minimized. So the input is just 2D key point, which we can obtain from raw data. And in testing time, we just minimize this 2D error, and we just optimize this parameter by minimizing this error. And as you can imagine, this may not work well because there can be multiple solutions in minimizing the 2D error, right? And to resolve this issue in this particular example, we use this prior. So we add this prior term, which is basically pushing the output in the plausible human motion space. And this plausible human motion space is modeled by other data sets, such as some other motion capture data set, where we can somehow define some, a common motion distribution of common pose. For example, in this particular case, we can use this particular data set where we can somehow measure the limit of human pose, and we can build this prior model, such as mixture of Gaussian. And in testing time, we need to minimize this 2D error, and at the same time, we need to satisfy this prior term. This works well if we have a good initialization, but there are a couple of issues. One issue is the prior doesn't consider any input. It's really prior. And sometimes this prior is conflicting with this 2D data term. So we need to do a nice balancing between this data term and prior term. Let's just take a look at how it works. So in this particular case, this person with this 2D key point is our current target. And unfortunately, in this case, our initialization is quite bad because there are two people occluding each other. So in this case, usually, in this SMPLify, usually this multi-stage optimization is used because it basically has lots of local minima. So in this particular example, we first try to minimize the torso part by just fixing other part, and then we optimize every part together. And this kind of multi-stage optimization works quite well in practice to avoid some local minima. But again, in this case, the result is quite not successful because prior term and data term are conflicting each other. And this is more specific example. So if you remove this prior term, the joint can be closer to our target, but the result is not realistic human pose. If you use this prior, it doesn't go to that direction, but still the output remains in the plausible human motion space. So it's easy to generalize because there's no training here other than that prior term we can obtain from motion capture data set. And we can, in testing time, given the 2D key point, we just optimize this model parameter directly. But there is just this issue like ambiguity in 2D key point input is slow, and a good initialization is really necessary. And there is just this balancing issue and so on.
Now let's consider another option where we use RGB images as input and we produce this 3D parametric model as output. HMR is one of the most popular models in this direction. So in this method, the model takes raw image as input and it produces this SMPL parameters, including pose parameter and shape parameter, and also the camera projection parameters as output. So now the question is, what kind of supervision we can use? Because if we only use this indoor environment, then basically the model may learn a strong bias of this data set. So in this method, it proposed a way to merge this indoor 3D data set and outdoor 2D key point data set, such as COCO. Most specifically, if we use this 3D data set, like 3.6 million data set, then basically we can use this 3D supervision. But we can still use some 2D key point supervision if we want to use this COCO data set. For example, if we use this COCO, then given the produced this SMPL parameters, by using the predicted camera parameter, we can basically project this model to image space that we can use this 2D loss between the projected skeleton and the 2D key point annotations. However, in this case, there can be some multiple possible 3D output, which can minimize this 2D reprojection error. So to handle such ambiguous cases in this model, they use this discriminator. And this discriminator is basically enforcing that the output can be within a similar distribution of this 3D pose data set. So by using this 3D data set and 2D data set, we can now train this model, and that works also outdoor environment because the model basically sees these outdoor scenes as well. So in practice, it works quite well like this. So in this raw pixel input, you can produce this kind of SMPL output. One of the big advantages of this method is because now the model used the raw images as input, it's actually quite robust. And robustness here means compared to the method like using 2D key point or dense pose input, although the image is a little bit kind of erroneous, like blurry or low resolution, still the model can produce some reasonable output. Some disadvantage here is because now we need to use this 3D data set and 2D data set, maybe the training is a little bit challenging, and also because the output is from the directly regression, often the output may not have good 2D localization quality. More recent work in this domain and this direction, which name is SPIN here, is proposing a bit interesting direction to improve the quality. This method focuses on the fact that in terms of 2D localization quality, the optimization method is better. And in terms of 3D, reachable 3D quality of the output, regression method is better. So in this method, it actually proposed a very, very nice way to combine these two properties. For example, it used a similar actually the same HMR model where the model takes the raw image as input and produces SMPL output. And we can actually further improve the quality of this one by using some optimization-based methods, such as SMPLify here. The benefit here is now, given a good initialization of HMR kind of network, we can further refine this 2D localization using the already provided 2D key point annotation. So we just run this SMPLify so that we can have better quality of 3D pose. Now, we just use this as a pseudo ground truth. So instead of using other discriminator, we just use this pseudo ground truth as supervision to train our network. So if there exists like 3D supervision, such as indoor 3D dataset, we can still use it. For 2D only dataset, we generate this kind of pseudo ground truth so that we can also provide supervision. And it turns out this method works quite well. It has this similar strength in terms of robustness as in HMR, and actually it has better localization quality. One cons here is maybe the training is still a bit challenging because now we need to run this SMPLify in the middle of this training stage. So given the nice success of this scheme model where pseudo ground truth can be used as a strong supervision, we may ask something like the following question. If there is another way by which we can make a better quality of pseudo ground truth for in-the-wild 2D dataset, then probably we can leverage this pseudo ground truth dataset so that we can train the model from scratch. One recap here is, let's go back to SMPLify and let's consider what SMPLify does. So given the input image, especially in spin example, it used a already trained 3D Pose Regressor to make a nice initialization. Then given 2D Keypoint annotation, such as Coco dataset, it runs this optimization so that we can get a better 3D SMPL parameter. So in this case, the optimization is really focusing on this part. It ignores all this input from the initial parameter, and given this 2D key point, it just minimizes this error. Of course, the 3D can be erroneous if you only focus on this 2D error. So in SMPLify, we use this prior term. The problem is, in this optimization, sometimes the result can be even worse than the original one because this optimization doesn't consider any input information. It's really dependent to this prior. And sometimes prior may not be agreeing with the input data. Then it actually provides some artifact, making the result worse. It actually happens in spin. So in our very recent paper, which name is example fine-tuning, we have a bit different way to parameterize this optimization framework. So instead of using user prior term-based optimization, we just retrain, we just fine-tune this network given this 2D key point. More concretely, so given a already trained 3D Pose Regressor, we can, given the input, we can initialize this parameter, the same as spin. But now, instead of using SMPLify, given this 2D key point loss, we just backprop here this to the network so that we can fine-tune this network. And we do this fine-tuning for just one sample, this current sample. And then, because the network is taking the input image as input, and still it is minimizing this error, it turns out this regressor keeps a really interesting 3D pose prior information, which is conditional to this input. So after a few iterations, like 20, we can get pretty reasonable 2D loss, and still the 3D doesn't break. Still, 3D is still remaining in a good plausible pose space. And then our final output is just by just direct output of this fine-tuned version of regressor. So given the same input, just fine-tune the version, and this final optimized parameter. The final parameter is our tuned parameter, which has better localization quality than this initial version. And after applying this EFT for one sample, we just throw away this fine-tuned one and redo the fine-tuning for the next sample. So let me just show you some qualitative comparison here. So this is SMPL model by using SMPLify, and this is the initial result given this input image. And in this case, this is quite challenging because now there are two people uploading each other. So initialization of this HMR is quite noisy. And now we run this SMPLify process by this multi-stage optimization. And as you can see, although we can minimize this 2D error, still the 3D doesn't look correct compared to our target person. With the same input and same status, you can see that this EFT works better. Note that EFT doesn't use any explicit prior. It just fine-tunes the network, and we just believe that the network has this nice property to keep the output in a plausible human space. This is another example. This is SMPLify. Again, the initialization is quite bad because the scene itself is quite challenging. And in this kind of case, although we use this multi-stage optimization, the result is not great. While EFT converges more efficiently, and the result quality is much better. So we can use this EFT technique to produce a better quality of pseudo ground truth. Especially, we do this for entire COCO data set. And now we have a nice pseudo ground truth for the COCO data set. And then we can just use this nice pseudo ground truth to retrain our network without using any other complicated technique, right? And this is some quantitative evaluation. So now we are evaluating the performance in this outdoor 3D PW data set. And this error is basically mean per joint position error, just computing the average error between the ground truth 3D and the predicted 3D. And when you see the number, this is the spin, which is the state of the art. And in this network is trained with multiple data set. For example, indoor 3D data set and outdoor 2D data set. And now we just train the same network with just only COCO data set using our pseudo ground truth. And actually the quality becomes better than this previous state of the art without using any other complicated technique. So this is very useful because now we can train the model without making complicated combination of indoor and outdoor data set, but we can just use this pseudo ground truth as a supervision. Now let's move on to other input and output options. So in this case, our input is still the raw image, and as output, we generate some key map representation instead of directly regressing the SMPL's parameter. So monocle total capture paper is one of such direction, and this is its output. So as output, this model produces parametric models output, but in this case, the model also generates face and hands motion as well. So this particular parametric model is the other model we presented. So let me briefly describe the method. So instead of applying some regression kind of method, we somehow use key map representation because we got really nice lesson from 2D Keypoint estimation domain where key map actually produced pretty nice 2D localization quality. So we consider what would be the corresponding 2D representation to represent some 3D information. And the idea here is now we consider some unit vector to represent each limb part, for example here. And then we just represent this number, the orientation, unit vector's orientation into the heat map orientation. So for example, now we are considering this particular limb, and we just embed this, this value to this heat map representation. So if we can generate this kind of output, then we can convert this output to this XYZ orientation by which we can actually generate this kind of 3D information, which we call as part orientation field or POF. And in this case, we use a optimization technique so that we can fit some parametric model, in this case, ADA model, to this computed representation. And in this paper, more interesting thing is now we can also apply the similar technique for hand pose generation. And we also compute some addition to the key point. And then we combine all this part in a single unified optimization so that we can have body, face, and 3D information. And to do that, we still need some nice training set because now our target is not only body, but including other parts as well. And this Panoptic Studio dataset has body and face and hands information together, and we leverage this dataset. And this is some output. So the left, you can see the input, a single view video, and as output, this model produce body motion, facial expression, hand motion. If our target is to obtain both body and hand, then maybe you can use a bit simpler and more efficient way. And this Frank mocap is a paper we recently published. And in this case, we just use regression and simple integration approaches. For example, we build a body model, a 3D pose regressor, and similarly, we can also build a 3D hand pose regressor. So we get hand pose and body pose. And then we can simply merge these two parts into the same single unified model framework, such as SMPLX. This is some example of our hand pose regressor. So in this particular example, we just use a very similar HMR kind of network so that we can, so that the model can take a raw image as input and produce this 3D hand pose parameter as output. And this is the combined version. And you can see on the right, that is the output of our Frank mocap. And you can see the comparison with MTC and SMPLify-X method. The major advantage of this method is very fast. So in this particular example, one frame takes about 1 second, which is orders of magnitude faster than other method. And we can use actually a bit more efficient method. So in this live demo, it works even almost kind of real-time performance. So you can see on the output, it reconstructs body and hands together.
Now let's consider our last option in this tutorial. Now it takes an RGB image as input, and we produce 3D volume as output. So this Pi3 HD is one of such direction where, given a single image input, we generate this full 3D volume as output. And in this particular method, we use this implicit shape representation. More specifically, instead of explicitly defining the output representation, here we only build a function, and this function takes the image feature and the 3D location as input and produce the occupancy information as output. I'm not gonna get into the details, but this Pi3 HD is based on the original Pi4 paper by Saito et al. And in this Pi3 HD, we introduce multi-level approaches so that the model can take the larger resolution images as input to produce more detailed 3D information. These are some example output. So this is the single image input, and now we generate the 3D volume as output. Note that this method is based on per frame processing. So there's no temporal smoothing and so on. So far, we have seen some interesting 3D human reconstruction approaches. But now the question is, can you also go beyond just a human 3D reconstruction?
So we present this paper in this ECCD, which name is FOSA. And in this paper, we reconstruct not only the human, we also try to reconstruct this 3D object together. Especially, we are focusing on how to place them in the same 3D space. This is more example. And for more details, please see our paper or please visit our poster session. So let me finish this tutorial with some interesting problems. So in the end, we really need a large scale in-the-wild benchmark so that we can evaluate all this method. Reconstructing body, face, hand together would be still very interesting direction because basically humans use all this part in our real body gestures. Reconstructing multiple people and finding their spatial arrangement is still very interesting direction. And also combining this 3D pose reconstruction and 3D shape reconstruction in the same pipeline can be another interesting direction. And also reconstructing 3D humans and 3D objects, especially all this work, would be very interesting direction. So you can see all this paper I mentioned in these references, and thanks for your attention.